Okay, in this example, we are now going to be looking at some expressions that have variables with exponents in them. Now, like I've said all along, just remember the same rules still apply. You've been working with exponents with numbers. Now we're going to be working with exponents with variables, and all the same rules apply. So let's just go through each one of these one by one. So in this first one, part A, we're taking the fifth root of this whole expression down here. 4a to the 8th, b to the 14th, c to the 5th. Now remember, when you're simplifying radicals that are not perfect roots, what you're trying to do is factor out the largest perfect root factors that you can. So when you do like the square root of 72, for example, you factor out 36 because that's the largest perfect square in that in 72. So here in your variables, you're going to have to look to see what the largest perfect square is, or not perfect square, perfect fifth root. Now these are actually pretty easy because with your variables you don't have to think about all of the different factor pairs. You know that the only factors of your variable are the variable itself. So when we look at part A, we've got 4, and then we've got a to the 8th power, which means we have 8 a's. We have b to the 14th power, which means 14 b's, and c to the 5th. So the factors that are going to be perfect fifth roots are all exponents that are multiples of 5. So what we want to do is we're going to rewrite this with factoring out all the perfect fifth powers from each term. So you'll see right here, if you look, we've taken a to the 8th power and we've rewritten that as a to the 5th times a to the 3rd. We've taken b to the 14th and rewritten it as b to the 10th times b to the 4th, and c to the 5th is a perfect fifth power. The reason we took out the a to the 5th and the b to the 10th is that those are the largest perfect fifth powers from that variable. So a to the 8th, there aren't 10 a's, so we can't take out a to the 10th, so a to the 5th is the largest fifth power we can take out. Now, what we're going to do is we're going to go ahead and we're going to split up our radical. We're going to have the first radical just contain our perfect fifth powers, and the second radical contain all of the non-perfect fifth powers. Now obviously 4 is not a perfect fifth power, and there are no multiple factors of 4 that are perfect fifths. So when we split this up, you'll see in the first radical we just keep all of our perfect fifths, so a to the 5th, b to the 10th, c to the 5th, and then in the second we have all of the non-perfect radicals. Now we go ahead and we can evaluate the one on the left. So the fifth root of a to the 5th is just a, the fifth root of b to the 10th is just b squared, and the fifth root of c to the 5th is just c. So when we evaluate this, we get ab squared c times the fifth root of everything that we weren't able to factor out. So it's very simple. Again, when you have variables with exponents, just remember you're trying to factor out multiples of whatever your index is. Okay, now in part B, we need to simplify this. The problem with this is we have a radical in our denominator, and we can't have that. So in order to simplify this, we need to turn y to the 8th into a perfect cube so that we can simplify that and get rid of the radical. So first thing you have to do is figure out what do we need to multiply y to the 8th by in order to turn it into a perfect cube. In this case, remember, our perfect factors are ones that are multiples of the index. So our perfect cubes are going to be y cubed, y to the 6th, and y to the 9th power. So we need to multiply y to the 8th by y to get y to the 9th power. Now remember, we can't just multiply it by y, we have to multiply it by the cube root of y because we need to turn our radicand into y 9th. So it's going to look like this. We're going to multiply right here both our denominator and numerator by cube root of y. When we do that, we're going to get cube root of y to the 9th on the bottom. Now, that is a perfect cube, and when we simplify this, we're just going to be left with x times cube root of y on top and y cubed on bottom. We can't simplify this anymore. Now again, the key right here is when you multiply this, you can't just multiply it by y. You have to multiply it as a radical with whatever index your original problem has. Okay, on the last one, this is where we have a fraction with multiple terms in it. And what we need to do is just use our properties of exponents to go ahead and simplify these problems. So what you're going to see here is that we've got a fraction that has x's, y's, and z's in it. Now, we need to go ahead and cancel out any common terms that we can. And here with z to the negative 6, we need to turn that positive. So what you're going to be looking to do on this is you're going to have to go ahead and go through one by one and cancel out and try to simplify each like term. So as we go through this, we're just going to start doing some of the work up here. First of all, you want to simplify your coefficients. So you know that's going to be 7 on top. I'm just going to draw this as one big fraction. So 14 and 2, those cancel out to 7. So I'm going to cross that out. Now you go to your x terms. We have x, this is the same thing as x to the first. We have x to the first over x to the 3/4. What we get there is just x on top. And remember, we have to subtract. So we get 1 minus 3/4. That's subtracting our exponents. So we're going to get 7 times x to the 1/4. Okay, so x to the first over x to the 3/4 is just x to the 1/4. That gets rid of that. Now, y to the 1/3, there is no other y term, so we can't simplify that at all. So that just becomes y to the 1/3. That stays as is. Now, in our denominator, oops, now we've gotten rid of that. In our denominator, we have z to the negative 6. Now, there's no other z terms to try to cancel out, but if you remember from class, we talked about when you have a negative exponent, in order to simplify that, you need to take your base, move it to the other side of the fraction, and then turn your exponent positive. So that means this z to the negative 6 in our denominator is going to come up to our numerator, and we're going to have z, and our exponent turns positive. It's going to be z to the 6. Now we go ahead and cancel that out, and now we've simplified everything. Now in this case, there is no denominator for our simplified form. Everything in the denominator was able to cancel out. So our final answer is going to look like this right here. 7x to the 1/4 power, y to the 1/3 power, z to the 6. Again, the key with these problems with multiple terms and multiple variables is to just go through like term by like term and just simplify each one individually. X's and Y's can't cancel each other out. Non-like terms can't cancel each other out. So you always want to make sure that you're just going through like term by like term and simplifying each one individually until you eventually simplify every single term.